Okay, so here's where we left off. So we had some trouble with the proof of linearity for step 3. And the trouble comes from the fact that when you try to apply the standard way of approximating x and y, and also ax plus by, so you have no issue with the approximation of x and approximation of y, but you have an approximation of ax plus by using the approximations of x and y. So indeed, the nth order approximation of ax plus by is not equal to a times the nth order approximation of x plus b times the nth order approximation of y. That was the trouble. But still we have a z1x plus b z1y less than a z2x plus b z2y, etc., etc. They are all simple functions. And the limit of znx plus b zny is still ax plus by. It is just not the standard way of approximating ax plus by. It is another way of approximating ax plus by. So we would conclude that the integrals of these approximations converge to the integral of ax plus by, and the proof would be complete if we had the following theorem. So I'm going to close the proof here and state a theorem, and that theorem will do the job, okay? If you have not the standard but any way of approximating a function in terms of simple positive and increasing sequence of functions, then the integrals of those simple functions converge to the integral of the original function. So that's going to be the main theorem of the day. We're going to write it in short as MON, and it is the monotone convergence theorem. It is the most important theorem in integration theory. Okay, so I use x, yeah, okay. Let 0, x1, x2, etc. be positive measurable functions. Of course, their limit now exists because it's monotone. And let x be their limit. Then we have integral of x1, integral of x2, etc., etc. And the limit of the integrals is the integral of the limit, which is xn. Let me write it this way. X d. So if we had this theorem, take any increasing sequence of positive measurable functions, their integrals converge to the integral of the limit. Limit of the integral, integral of the limit. So that's called the convergence theorem. And since the functions in the theorem are increasing with respect to n, it's a monotone convergence theorem. Okay? That's the most important theorem. This is the most important theorem in integration. Okay? I'm going to put it in a red box. Okay? And we're going to have a lot of corollaries, consequences of this theorem. It's going to produce a lot of important results for integrals and expectations. And linearity is one. It already produced one important result. It's linearity. Why? Just let this be x1, x2, x3. They're increasing, right? x1, x2, x3. They're increasing positive. You don't even need being simple. Okay? Apply monotone convergence theorem. The limit of the integrals equals the integral of the limit. Limit of those guys is equal to the original function ax plus by. So the one very first consequence is that it proves linearity. It finishes the proof of linearity. Let me just write it. For instance, it finishes the proof of linearity. But later we're going to prove other consequences of it. Okay. So of course, now the question is, how are we going to prove monotone convergence theorem? Right? That's the next question. And for this, to prove this theorem, we really need to understand why this blue part fails and what else we can do. Okay? So is there a case where approximating x plus y is kind of linear? Can we write the approximation of x plus y is equal to the approximation of x plus approximation of y? Is there such a case? So if you recall, the problem was that x and y, just forget a and b here, okay? If you look at x and y, they have values on overlapping regions. So we cannot really approximate, while we are approximating x plus y at order n, let's say, we cannot really decompose it into the parts that belongs to x and that belongs to y. That was the problem. But if you have two functions, x and y, that have non-overlapping regions, let's say you have a random variable which takes value, a non-zero value here, and 0 everywhere else, and another function here which takes a non-zero value here, but 0 everywhere else, then you can approximate them together. Because it is just one value here and one value there. They're separate. Okay? So how to prove mon? Okay? And the idea is as follows. Let's say we have x, okay, positive measurable. Let me write it as a lemma, okay? Not idea, but lemma. And let BC be disjoint sets. Then x indicator B union C, the integral of this is equal to x, the integral of x indicator B d mu, integral of x indicator C d mu. So that is also kind of a linearity, but with disjointness. Okay? These two functions, x indicator B and x indicator C, they don't really interact. So I'm going to call it lemma for Mon. Okay? So the idea is to prove monotone convergence theorem without using linearity, because linearity is a consequence of monotone convergence theorem. But we need something that is still like linearity, but not the full power of linearity. We don't have the full power of linearity. We will just use this fact, okay? So in fact, you can define some notation. So if you'd like to integrate x over region B, this is how you define it. Just integrate x times indicator B in the usual way, namely on the whole omega. Okay? So in other words, we have x over B union C is equal to x over B and x over C. And let's prove it. Proof of lemma. So if you look at just Fn of x, okay, you can look at it in, or maybe let's say x indicator B union C, okay? So you can see it as x indicator B plus x indicator C, right? Because B and C are disjoint sets, so the indicator of the union gives you 1 if you are either in B or in C. The observation is that you have this equal to Fn of x indicator B plus Fn of x indicator C, because they are on non-overlapping regions. That's the main observation. If you'd like to approximate the sum, it is enough if you approximate x over B and x over C and add them together, because they are on just different regions. Therefore, if we write Fn of x indicator B union C d mu, this is equal to Fn of x indicator B d mu plus Fn of x indicator C of d mu. And if you let n go to infinity, this is going to converge to the integral of x indicator B union C. And this is going to converge to the integral of x indicator B and x indicator C d mu. Or you can write it this way as well. So we wrote the first equation because this is a simple function. This is a simple function. And this is a simple function. So here we indeed use linearity in step 2. And then we just let n go to infinity. So we really understood what was going wrong in the proof of linearity, and we created an easier version of it, which does not really use monotone convergence theorem. So now the idea is to prove monotone convergence theorem using this lemma. First of all, so this is proof of mon. Okay? So what do we need to prove? well, if x1 is less than x2, etc., then we automatically have x1 d mu less than x2 d mu, etc., right? So this part is for free because we already proved monotonicity. We just need the convergence part. So by monotonicity in step 3, we already have x1 d mu, x2 d mu, etc. And since each of them is less than x, we even have this. So each of them is less than x. Therefore, the limit of all those values which are below integral of x is also below the integral of x. So one part is not very difficult. It just follows from monotonicity of integral, not convergence. So the more involved part is to show the opposite. Limit of integrals is larger equal integral of limit. So what are we going to do for this? First of all, that's a positive measurable function. Let's recall how this integral was defined. So I'm going to call it Zn, Fn of x. We have Z1, Z2, etc., and the integral of x is just the limit of the integrals of Zn's. And indeed, the limit was increasing. Here?
No, at the one before the last one. Before Zn.
Yeah, integral of Zn d mu.
And don't we need another limit n from infinity between them?
Why? So Zn is just the standard approximations of x. Okay? So by definition, so this is definition in step 3. Right? So let me call it star. So star follows if we can show that this limit of integrals of xn's is above the integral of z d mu for every simple positive function z such that z is less than x. Okay? Let us try to digest what this means, okay? So xn's are arbitrary functions, not the standard ones that are approximating x. But on the other hand, we have functions that are approximating x in a standard way. These are zn's. What we know is that the integral of zn is always below, is always on this side, okay? So if we can show that for every zn we have this inequality, we just can let n go to infinity here and get that this limit is greater than the limit of integrals of zn's, which is just x d mu, because x d mu is defined as the limit of integrals of zn's. So it is enough just to take one simple function that is always below x, okay? It can be one of those zn, z1, z2, z3, and show for this z that this holds. So this is our whole aim, okay? Okay, so here's how we're going to do it. So it's a simple positive function, okay? Therefore, we can have a structure of it, right? It has a concrete structure. And indeed, it has a canonical representation. Let's write down its canonical representation. Let's say Z has the canonical representation Z equals Z1 indicator A1, Zm indicator Am. Again, this picture, Z1, Z2, Z3, Z4. And this is just the set Z equals Z1. This is just the set Z equals Zm. So in particular, A1 to Am are measurable disjoint sets whose union gives us omega, okay? So this way of decomposing Z into regions which are disjoint should remind us our lemma. By lemma for mon, we have what? Integral of Z is, well, just Z1 mu A1, Zm mu Am, and integral of xn d mu is integral of xn over A1, integral of xn over Am. So if we can compare them set by set, like this, then we can also add those inequalities and get an inequality for the whole integral. So it is enough to show the limit of the integrals of xn's over some aj is greater than zj mu aj as n goes to infinity. So this we need to show for all j. Okay. And here zj, let me say, if zj is 0, the result is clear because this part is just 0 and this is just limit of integrals of positive functions, so it is always 0. So assume zj is strictly positive, and we also have zj is less equal x of omega for all omega. And this is because z is a function which is always below x. If you look at one particular value of it, it is also below x, but not for all omega in aj. Okay? Okay, so now we will show this. Okay, and we have zj below x, the values of x on the region aj. So here's what is happening on a line. We have x of omega, and we need to somehow relate this stuff to xn's. So there is x1 of omega, x2 of omega, etc., 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 and they converge to x. and we have a point Z somewhere here. Okay, somewhere here, Zj. So if we have Zj equals x of omega, then we can still have xn of omega is below Zj for all n. So if Zj is indeed here, you can have all the approximating numbers still strictly below this point. But if you have Zj strictly less than x of omega, then we have Zj less than xn of omega for some n. So if Zj is strictly below x of omega, and since this sequence is converging to x of omega, there must be some value of n for which Zj is strictly below xn of omega, right? So that's a main observation. Therefore, we will proceed in two steps. So step A is that assume Zj is below x of omega for all omega in Aj. Because then Zj less than x of omega, or the event that Zj is less than x, simply means that Zj is less than x of n for some n. Of course, on Aj. Okay, for Aj, but this is simply Zj. Okay, let's leave it this way. We can also write it as Aj, right? Because this is already true on Aj. We just assumed it. Therefore, as you increase n, this number increases, and this sequence of sets forms an increasing sequence of sets. So by sequential monotonicity of mu under increasing limits, we have mu of Aj is equal to the limit of the measures of those sets. So we need to prove that Zj times that value is less than this limit. So let's multiply things by Zj. Just a positive number, so let's just multiply. So Zj times mu of something looks like the integral of a simple function, which just takes the value Zj on this region, right? So you can see it as limit of integral of Zj, indicator Zj less than xn, on Aj. So I separated two indicators. Okay. Now, this is less than, or this is less than xn on this region. Therefore, we can bound it by xn indicator Zj less equal xn d mu by monotonicity. Okay, monotonicity is still there. And this is just less than 1. So I can even bound them by just xn. Therefore, we're done with step A. We proved this for step A. All we have to do is to consider the case where we allow zj equal to x of omega for some omega. So now we just assume what we assumed at the beginning. No specialization. Assume zj is less than x of omega for all omega in aj. And our idea is to use step A, okay? So if you have zj, which is possibly equal to x of omega, what you can do is to decrease it slightly to get strictly lower values. So note we have zj minus zj over n, which is less than zj, and this is less equal x of omega. Let me write it again, okay? So maybe zj is equal to x of omega for some omega, but zj minus zj over n is always strictly below x of omega. Therefore, you can use step A. Use step A to get, let's just cheat, okay? So this is zj, but now it is zj minus zj over n times mu of aj is less than the limit of aj xn d mu. Okay. One apology. I shouldn't have used the same n with this n. Therefore, I will replace it by k. Okay? Just to avoid confusion. And all we have to do is to let k go to infinity so that this part just disappears. And this finishes the proof. Because we said it is enough to show this, and we really showed it. That was probably the longest proof that we will ever do, okay? So, but that's the most important theorem, as I said. It's going to have a lot of consequences that we're going to prove not in a very difficult way. So just digest monotone convergence theorem, okay? And see it as an important tool for you, okay? Why is it so important? First of all, it proves linearity. So now we're done with the linearity in step 3, okay? But it has other consequences. Okay, any questions? That was a long proof, and there are a lot of ideas. So just make sure to go over that on your own again, okay? But what we know is that we really used just monotonicity plus the easy version of linearity, not the full linearity, to prove it, and we were successful. Okay? So we proved monotone convergence theorem. So let's look at some consequences, okay? Some corollaries. So some consequences of mon. Linearity in step 3 is now done. Okay. So just wanted to repeat. B is that we can get an infinite version of lemma for mon. So this nice result, okay? So let me write it as a corollary. Let x be positive measurable. And you have disjoint sets, A1, A2. Let us define their union as A, okay? Then we have the integral of x over A is equal to the sum of the integrals of x over AIs. Okay? That's a nice result, right? So you have A1, A2, A3, separate regions. You want to integrate x over the union of all AIs. What you do is to integrate x on A1, x on A2, x on A3, and get an infinite sum. The sum of all those integrals gives you AI, the integral of x on the union A. And we will just prove it using Mon. So we have disjoint sets, and we need monotonicity. What is the idea? How do you get monotone stuff out of disjoint sets? So first of all, if we have disjoint sets, we always have a clear way of creating increasing sequence of sets, right? A1, A1 union A2, A1 union A2 union A3, etc., etc. And then we can just look at x at the indicators of each of those unions. So let Bn be A1 to An for each n. So we have 0 less than x indicator B1, x indicator B2, and the limit of x indicator Bn is the limit of x indicator A, because the union of Bn's is equal to union of AI's, and this is equal to A. I don't want to erase monotone convergence theorem, so I will erase this part. So by monotone convergence theorem, we have limit of let me first write integral of the limit. What is the limit? Limit is x indicator A is the limit of integrals of x indicator Bn. Okay? This is by monotone convergence theorem. Because x indicator A is the limit of x indicator Bn's. Now, what is Bn? Bn is a finite union. Where is it? Here. Bn is a finite union. Therefore, we can write it as x indicator A1 up to x indicator An, like this, right? And now we can use the finite version of the lemma. X indicator A1, X indicator A2, X indicator A3, we can just add them. X indicator A1, d mu, X indicator An, d mu, by lemma for Mon. So we're trying to prove the infinite version of it, so we need to use the finite version of it. Now, what is it? This is the limit of sum of 1 to n of integrals x d mu over ai. A1, A2, A3, An. And this was always n goes to infinity. So what is limit of n goes to infinity of summation 1 to n? This is by definition I equals 1 to infinity. So we proved it, right? 1 to infinity of integrals. Consequence A, B, now C. This is the series form of monotone convergence theorem. So let x1, x2 be positive measurable. Then the integral of the sum of all xi's is equal to the sum of integrals of xi's. I will leave this to you as an exercise. So this is called the series form of monotone convergence theorem. But look at the theorem. Look at the corollary. There is no monotonicity. x1, x2, they are not ordered. OK? No order. Okay. Another last corollary is the so-called Fattens Lemma. That's another important convergence result. Okay? So again, let x1, x2, etc. be positive and measurable. Then the integral of the lim inf of xn's is less than the lim inf of integrals of xn's. So that's only a one-way inequality. It's not an equality. So it's not as powerful as monotone convergence theorem. But the main thing here is that if there is no order, then there might be no limit. So if you have x1, x2, x3 just measurable positive functions, their limit may not exist. Okay? So before writing, at any time, before writing limit of a sequence, make sure it exists, right? So if we have monotone sequences, it always exists. But if you have an arbitrary sequence of positive measurable functions, their limit may not exist. In that case, at least you have a lim inf and a lim sup. So next time we're going to prove a version of this for lim sups. It's called reverse Fattens lemma. But this Fattens lemma is for lim inf. Okay? And let's prove it, okay, before we go. That's a nice important result. Again, the idea is to use what? Mon, right? Monotone convergence theorem. So recall lim inf is nothing but sup of infs of xk's, k greater than n in n. So just call it yn, okay? Just call it yn. Now, we know y1, y2, etc. And the limit is the lim inf. So monotone convergence theorem implies y1 d mu, or in general, yn d mu, the lim of yn d mu is equal to the integral of the lim inf of xn d mu. On the other hand, yn is just the inf of xk's after index n. So yn is smaller than each of them. So the same is true for integrals. Therefore, if this is true for all k greater than n, you can also write yn d mu is less than the smallest of them. So let's bring the two together and conclude. So we have this And this 1 and 2 gives us what? The integral of lim inf xn d mu is equal to lim of integral of yn d mu. Each yn d mu is less than the inf of xk d mu, k greater than n, and now n goes to infinity. And this is indeed the lim inf. So we can just write lim inf x n d mu as n goes to infinity. Right? Integral of lim inf is less than the lim inf of the integrals. So Fattens Lemma is an important convergence result, okay? There are three big convergence results. One is monotone convergence theorem. The other one is Fattens Lemma, although it just looks like a corollary that is squeezed here. It is another important convergence result. It is important because it exists in the case of the non-existence of limits. So even if you don't have limits, you can talk about lim inf, and that's what you have in that case. The third will be dominated convergence theorem, but for that, we need to first extend our definition of integral to arbitrary measurable functions, namely functions with positive and negative values together. So that's the task for the next time. Okay? Thank you.